Good evening. Okay, let's start our third class. Let me share my screen. You can find a notebook for today in the Telegram chat. There is a notebook. This one. Today we'll have a bit theory because there were no lectures after our after the first and second classes. Yes, schedule a bit strange. Your second deadline is for DataChem course. We will send a link to this course today or in the next couple of days. Okay. Today we'll talk about cross-validation and grid search, stationarity and integration in the context of ARIMA models. And at the end, we'll generate random walk, moving average processes, and autoregressive process. And test whether they are stationary using KPSS and Dickey-Fuller tests. See a question.
I just would like to ask you, or there are no any grades. Just if you done it, you get some percent in total.
If you complete the course, get 10. If you didn't complete it, 0. Just 2 grades, 0 or 10.
Thanks.
Okay, let's see what we now can do. Like the first and second classes, we split the data into train and test. Now we will use more complicated technique. Well, let's repeat. First, let's repeat test and train split. It looks like this. We split the data into test and train. Now let's see what we will get if we. I need to run this code. Okay. Let's add the following loop, and we will see like to understand the idea of cross-validation. Let's add for I in range. Let's take 5. Not forget to use tabulation. Yeah, and just run the code. Okay, LT show. Okay, you see, we can like use the same data, but estimate different models 5 times instead of just one, we can use we can obtain 5 times more scores. What can be a score? In the previous class, we studied, for example, mean squared error or mean absolute error or mean absolute percentage error and so on. So instead of just one computation of a score, you can compute it many times and calculate the mean value, average value of a score for each step. Okay. What are the benefits of this technique? Well, for example, if we use 2 models and one model is the best for this data, it can be just a coincidence. So it can be good for this test and train split, but very bad for another test and train split, and so on. The score can be different. And instead of just one score, we want to use average score. It is much better. Okay. And the idea is represented in the following picture. Okay, if you want to include the picture into your code, you can use delete dots, use the following structure. Okay, and here is the link to the picture. Okay. As I've already said, you estimate the model each step and calculate average score, and then choose the best model according not just to one score, but according to average score. Time series cross-validation, it is not just the only type of cross-validation. For cross-sectional data, K-fold cross-validation or stratified K-fold cross-validation can be used. Just additional information for you. We won't use these procedures in our course. The main difference is that here test can be before train, and it is not possible. So we can use we cannot use test for what we predict, what we want to forecast before our data. Our test set is always after train data. Okay. So it's not applicable to time series. Okay, let's proceed. Now this function, we know this function, and sliding window splitter and forecasting grid search CV is our new 2 functions, and we will use them today. Let's run this code. Now, we specify a model AutoETS, but here we add only seasonality period, and like we don't include here type of error, additive, or for example, multiplicative, or type of trend, and you will understand soon why. Okay, these are two. These lists could create two lists for losses and grid CTS. But we can delete them because we want. Sorry, we are not going to use them. Okay, now let's. This is our first function for cross-validation, time series cross-validation, for splitting the data many times. Okay, and now let's use forecasting grid search CV. Inside this function, we need to. So the first argument is our model. It is called, in our case, model. Okay. The second one is like a type of cross-validation. In our case, it is CV uppercase. And the next argument is param grid. And here we need to add hyperparameters for our grid search. And okay, second. I got your question about dictionary, why this like param grid, why it is in the form of dictionary, not list. So because I think because it is easier to represent like this argument. I cannot imagine how you can represent this dictionary as a list. Let me explain you. We will what it means. Okay, grid search will apply search. Let me explain the concept of grid search. This model will estimate all combinations of hyperparameters. These parameters are called hyperparameters. For example, we have error, additive, and multiplicative. And the same for seasonality. But for simplicity, let's assume that a seasonal component is fixed for us, and we look the best combination for error and trend. And the model estimates all combinations. For example, additive trend and additive error, and multiplicative trend and additive error, and so on. And this form is, it looks like a grid. That's why it's called grid search. We calculate a score in each for each combination, and then choose the best model according to the score. Now it can be only in this. These brackets called braces, if I'm not mistaken, and you must use braces because this object it must be a dictionary, in the form of dictionary. Why? Because for each hyperparameter, we need to set possible values of okay, Dmitry, is it a question or?
No, it is my notes from Data Campus course.
Okay. Thanks.
We have several people who did not work early in Python, and
yeah.
we don't know difference between curly breaks, square breaks, and so on.
Okay. Just memorize that for param grid, you need to use curly braces because this object, like this argument, should be a dictionary. Okay. Okay. Let's do it for trend and for seasonal component. Okay. GSVT, which is the name of our model, and we apply method feed to feed the data inside brackets, and our data is Y. And now let's create a data frame for the results. It is a pandas object. It is a short notation for pandas. Okay, pandas data frame. And yeah, and now we want to obtain results of our model. And to do so, use CV results. Okay, and okay, let's see. Results of cross-validation and grid search. So now you can understand why it is useful to use grid search. Last time we estimated only one model, or new home assignment it was 2 models. Now we can see the score for each combination of error, seasonal component, and trend. Okay, and the best model okay, Anna, could you send a screenshot or yes, screenshot. Like check your code. Should be it should work. Okay, just remove sharp before this function, delete it. Okay. For the better representation, let's sort our results according to rank, of like each model. To sort, let's use the following function: sort values by and here's the name of the column. In this case, it is the last column. And well, let's see the results. Well, the best model is AMM. Okay. Has the lowest forecast quality metric, which is used here. Okay, and the score for test. Okay, not for train. Okay, what else? We can include here seasonality periods, and so we used 12. Let's try 12, 24. And here we can include only hyperparameters. Just in 1 minute, I will explain the difference between hyperparameters and parameters. Okay, as you can see, 12 is better than 24. Okay. You can try 6 or other values. And include other hyperparameters. Let's see our code from the second class. Okay, it is a summary for ETS model. Parameters which are estimated, for example, initial level or smoothing seasonal and so on. They are parameters. All of these parameters. What we estimate in the model are parameters. At specification of the model, hyperparameters determine the specification of the model. For example, hyperparameters are types of error, trend, and seasonality. Okay. Okay, let's continue. The next block is dedicated to stationarity and integration concept. They are building blocks for ARIMA class models. Okay, so they are very important for our next topic. First, let's discuss the difference between data generating process and time series. Data generating process, as it is written here, it is some stochastic or random process, and we don't observe it. It is something we want to know, and but actually we observe only time series. Time series is one trajectory. Yes, Konstantin, like to estimate this model, we need to include here none, okay, or this none. Let's check. So none this uppercase or lowercase. I don't know which one is right. Yes, this none. Okay. Now time series, so I've said it is a realization, and we observe time series. It is like some trajectory. One stochastic process can generate different trajectories, but we observe only one. Okay. And we want to use observed data time series to estimate the coefficient to determine the correct data generating process. Okay. And our final goal is is predictions. Let's recall the concept of stationarity. There are weak stationarity and strict stationarity. Weak stationarity is about moments. So the first moment is mean value. And according to time series is weakly stationary if mean value does not depend on time. Or if you take mean value for time period t and for time period t minus j, these values should be the same, okay? And the same for variance and covariance, okay? Weak stationarity is also called covariance stationarity. And there is a strict stationarity. For strict stationarity, time series in different time periods must have the same distribution. But it is not strict definition. Strict definition includes random vectors and like other complicated stuff. So we are not going to use the strict stationarity. It's like, just for you to know that it exists. Okay. Why do we need stationarity? Well, non-stationary time series is has, for example, this structure. Not the structure, the structure of such a time series at different time periods are not the same. And if we observe some data for some period, we cannot say anything about the future because the structure is not the same. And stationarity says that structure is the same for different time periods. That's why we can use current values, current observations to make predictions. Stationarity is very important. Okay. Integration. Okay, what is integration? Suppose we have like non-stationary yt. It is not stationary. How to transform it to stationary time series? We can, take differences, and if after the first difference it becomes stationary, the order of integration is 1. Okay. Let's consider an example. Yt is 0, 2, 4, 5, minus 10, 12. And time is 0, 1, 2, 3, 4, 5. Yt minus 1, delta yt, which is written here. It is, let's start from the end. It is K22, 12 minus 10, and is 12 plus 10, minus 10 minus 5, minus 15, 5 minus 4, 1, 2, and 2. Okay, it is the first differences. Okay, and if it is stationary, then the order of integration 1. If not, just continue taking differences and the number of steps after which the resulting process is stationary is the order of integration. Okay, for financial data, usually the first order we can deal with first order integration processes or second order integration processes. Okay, not more than 2. Okay, it is enough to take 2 differences. Okay. Now about Riemann representation. For the ETS models, we use decomposition into error, trend, and seasonal components, right? But for Riemann, we need the following form. It is a bit complicated, and that's why it is it started after ETS. Okay, what we can see here? Let's start with the Lac operator. Lac operator L. Applied to ZT equals ZT the period t minus 1. L to the power of 2 moves index 2 periods to the past. The power can be negative or positive. If it is negative, it moves our observation to the future. And like operator applied to constant is constant. Okay, let's consider its part separately. For example, for the error term, we multiply error term, like this bracket, by error term. And we get error term, this 1 multiplied by error term, minus this sum, okay? And the same for ZT. Okay, it should be noted that ZT here is stationary. But first, we need to transform our time series, take differences, or use other techniques to obtain stationary time series. And then, if it is stationary, we can use the following representation. And these coefficients, this is what we want to estimate. Sorry. Okay. Now let's consider the stationary form of this process. The process has stationary representation if we can represent it in the following form. Okay, if this sorry. If this value is just a constant, for example, 5, okay, 5 to the power of 1 is, to the power of minus 1 is 1 divided by 5. Okay, to the power of 2 is 1 divided by 5 squared. The problem can be with like not just complicated objects. And let's see what is written. What's written here? Oh. Okay, do you remember the value of infinite sum? Plus r to the power of n plus infinite number of r. Okay, and this sum is equal to 1 divided by 1 minus r. Okay, and yes, let me check. Yes, and it exists if r is less than 1. For r greater than 1, this like this sum equals infinity. Okay, and this like the result we obtained is like 1 minus r to the power of minus 1. But we want these coefficients to be like this, their sum should be less than 1. Okay. It is like the first criteria. We will discuss it in details next time. Yes, I want to explain you the logic why this representation cannot exist, and this is because the presence of these coefficients, not present, but for some values of these coefficients, this sum is infinity, and our series is infinity multiplied by something. Okay. The augmented Dickey-Fuller test, which we will have at the end of our class. Just let me show you. Yeah, Dickey-Fuller test. It checks like the sum of alphas, the sum of alpha 1, alpha 2, and so on, alpha p. It compares it with one and tests whether it is close to 1 or not. Okay, now okay, let's generate different processes. Let's start with random walk. It is not stationary. We can understand it as looking at its form, the coefficient here is 1. It is not less than 1. Okay, let's generate. First, let's create, let's plot one trajectory. Okay, we need array of normally distributed random variables. Why normally distributed? Okay, because it is written that yt random term is normally distributed. Okay, random normal. Scale is standard deviation, but here is variance. Okay. Just take a square root of this value. The square root of 1 is 1. Or I can use 1. Size is t. T is the number of periods. Okay, and let's create a NumPy array for our trajectory. It will be filled by it can be filled by any values. Let's use non-values. It can be any values. What is written here? We create an array which consists of the following values. For example, if instead of np none, it will be, so if it is 5, then we will get 5, 5, 5, and so on. 5 t times. In our case, it is 1,000 times. So we create an empty array to fill this array at the next step. We know this starting value. Starting value is just 0 element. The first element in Python is 0. It is x0. And now, okay, let's use loop for in the range 1 from 1 to t. It's a xt at time I equals xt at time I minus 1 plus ut at time I. This is equivalent to this functional form. Why? Because we want to generate random walk. So xt equals previous value I minus 1 plus current shock, current random term. Okay. And let's visualize it. PLT plot, xt is our trajectory. Yeah. Okay, we generate one trajectory. It is random. That's why we could get different trajectories every time. Now let's plot not only one trajectory, but many trajectories. Use tabulation and loop 4. In range and so for example, let's plot 10 trajectories. Okay, it's 10 trajectories. Moreover, we can include color option. Call np random uniform. It means that call is a uniformly distributed random variable with parameters 0, 1, standard uniform distribution. Now you will see why we want to use this color. Okay. You just to change color. Yeah. It is a random walk, and it is not stationary. Why? For example, let's look at this part and this part. They are different. The structure, for example, here variance is much greater in this part than in this part. Okay, they are not similar to each other. But it is not formal proof. Formally, we need to use different tests, for example, KPSS or Dickey-Fuller. We will use them later. Yeah. Okay. Now let's transform random walk in such a way. So we want to work with stationary processes, stationary time series. Differences for random walk is just random term ut. Okay. To visualize it, we can use code. Just copy code for random walk and delete this thing here, because our trajectory is just ut. And if you visualize it, you'll get something stationary. On different blocks. Sorry. On different blocks are like very similar. Okay, now. But again, it is not formal proof. It's just usual check. Okay. Now we have the next process is autoregressive process. The only difference is that we have a new coefficient before xt minus 1. It is beta. Let's add beta here. And run our code. Depending on the value of this coefficient, the process will be stationary or non-stationary. If it is greater than 1, for example, 1.00001, it is not stationary. Okay, if we take 0.89, it will be stationary. Okay. Okay, for beta less than 1. Now let's generate moving average. As you can see here, we don't have legs of x as in autoregressive process here, like here. Okay. Let's change our code. What is different? Instead of xt, we have ut. The time I t minus 1, I minus 1, multiplied by our coefficient alpha. Okay. And this process is always stationary for any values of alpha. Or we can take 1 or 500 and so on. Okay, for any values. Now let's choose, for example, let's take autoregressive process. Okay, and check whether it is stationary. Okay. To do it, we need this function add Fuller. And inside it, just use, we don't need plots. We want to apply it to our trajectory, our time series. Trajectory is time series, xt. Okay, it returns test statistic, p-value, and so on. We need only this, the second argument. So in Python, we need to use 1 and this p-value. For the confidence, for the significance level 5%, we need to compare it to 0.05. If it is less than 0.05, time series is stationary. In statistics, we would write the null hypothesis, and here it is that time series not time series, okay, time series is not stationary. And if p-value is less than 0.05, we reject the null in favor of alternative hypothesis and reject the null. The process is stationary. Okay. The second test is called KPSS test, and it has a bit different null hypothesis. It is opposite. It says that time series is stationary, and in this case we need to compare our p-value KPSS. This is the same number, but we need to change the direction of this sign. Okay, if it is greater than 0.05, we don't reject the null of the process is stationary. Konstantin, for what process? At Fuller, augmented decay Fuller shows false. And what is the value of beta? What value do you use? Okay. Maybe it is okay. We need to. We can find a threshold for. So maybe because it is close to 1. Okay. If we let's use 0.05 89 and change significance level. It will be true. Or it is close to 0.05. That's, yeah, it is very close to false. No, sorry, false. Okay. Yes, it was a stationary process. Okay, I know why. It's because the number of observations. Let's increase and repeat. Yeah. Yes. No, they can be non-stationary. It depends on the value of beta. Moving average is always stationary. Autoregressive process, stationarity of autoregressive process depends on the value of betas. Okay, for example, if it is greater than 1, you get false. But for 0. It is true. Okay. Simulations can be non-stationary. We simulated random walk. Random walk is non-stationary. We generate different processes. Yes. If beta less than 1, it is stationary. There is some problem with this KPSS test. Sometimes it doesn't work. Okay. Okay, I have a task for you. Well, now you can practice generation of different processes. For example, try to generate a moving average process of order 3 and autoregressive process of order 2, and combine the moving average and autoregressive process to generate ARMA, the following process. Time series from the following process. 2 is used for AR part and 3 for MA part. Therefore, we have 2 legs of our time series. Our autoregressive part is 2, and 3 parts for legs of error term. Okay. Okay, that's all for today. I'm waiting for your questions. Try to generate processes or ask questions about cross-validation, grid search. about RMAP representation, stationarity, and so on. Yeah, go ahead, ask your question about home assignment. And what is the question? Okay, let's return to our second seminar. Let me open home assignment. Yeah. Yes. Auto ETS. Okay, this is because okay, there are different functions in Python. For example, here it is the ETS model from ETS model from stats models, time series analysis, TSA, exponential smoothing ETS, and this auto ETS is from SKTime forecasting ETS. They are different, and they have different arguments, and so we need to use them differently. Okay. For auto ETS, we specify these hyperparameters and data inside fit, but for ETS model from stats models and so on, we include the data into the model. So it is the right answer. Yes, this, so fit is enough. Yes, we can, but we use this line because we want to obtain predictions. Fit means estimate coefficients. For predictions, we need coefficients. The estimate coefficients and like use them to forecast. Any other questions? Okay, that's it for today. Have a nice weekend. Bye-bye.